All right, thanks for having me, everyone. I'm going to be talking about the basics of carbon sequestration, kind of starting with the different types of sequestration, the reasons for doing a sequestration project, the components of a capture project, and how a project comes together with an emphasis on the geologic storage aspect. So what is carbon sequestration? Carbon sequestration is the process of capturing and storing atmospheric carbon dioxide to mitigate climate change. CO2 is a heat trapping gas, and it's produced naturally and through human activities. Man-made sources of CO2 result from burning fossil fuels and other industrial activities. And CO2 is also naturally released biologically through oceans, decomposition of organic matter, volcanoes, and forest fires. So for millions of years, the Earth was in a balance with a natural carbon cycle as carbon, dead things, were buried in the subsurface, dinosaurs and the like, were buried in the subsurface, and through geologic processes and time, the carbon becomes the fossil fuels that we use today. So everything was good, everything was cool, and then we hit the Industrial Revolution. And so now we're extracting the fossil fuels and releasing the carbon back into the atmosphere a lot faster than it was naturally being stored. So to help that process, we're now focused on putting carbon back into the ground. A lot of work has already been done on biologic sequestration through forest and soil management processes, such as biomass removal. But with natural hazards like forest fires and the changing political winds, both of those can undo any progress in an instant. So geologic storage, that's the process of capturing CO2, compressing the CO2 emissions, or capturing and compressing direct air capture, often called DAC, and pumping that captured and compressed CO2 into the ground as a supercritical fluid. It goes into the ground using using wells that are directed into a subsurface reservoir. And these are usually the same rock types where it was originally stored, such as a depleted oil and gas reserve or saline aquifers or unminable coal seams. But unlike biological storage, geological storage has engineering controls and is regulated, so it should be secure and is designed to be secure for 10,000 years or more. So nearly all countries signed the 2015 Paris Agreement to keep the rise in global surface temperature at or below 2 degrees Celsius. The aim is to reduce greenhouse gas emissions and reach net zero by 2050. The US has put significant investment into tax credits to help advance goals, but the intent is for the free market to take over and have compulsory sequestration by emissions driven by public demand. Enhanced oil recovery will also help sequester some volume of CO2, even as it brings new material to the surface. This will be needed as oil and gas companies begin to work through the expected energy transition as they go away from fossil fuels. So who is carbon sequestration right for? All CO2 emitters should review their emissions goals and see if a sequestration project would benefit their businesses. Projects seem to develop in two ways. Those with on-site emissions that are large and have the appropriate geology for on-site storage, such as some of the major oil and gas players in the Gulf Coast. And then others are those who are interested in bridging the gap between ideal locations and emissions to create a carbon capture or storage hub. Hubs bring together multiple streams of emissions from different facilities, and generally cleaner and more pure streams of CO2 are far more economical to capture, but they're generally smaller in volume and couldn't support their own injection facility, even if they had the appropriate geology. So CO2 injection into the subsurface has been used since the 1970s, when captured CO2 was injected into oil fields where recovery had decreased. It's common for oil fields to inject brines that come up from oil production, but CO2 floods reduce the viscosity of the oil and improves the recovery process. The volume of CO2 pushes the oil toward recovery wells, and then it comes back to the surface as oil is pumped up. The CO2 gets recovered during the process. It gets skimmed away from the oil, and the brine that's recovered, it's stripped out and then injected over and over again until the field gets abandoned. In the 1990s, research began to figure out how permanent storage could be achieved under the same principles as EOR. And over the last quarter century, significant progress has been made along with taxpayer investment. As the case for climate mitigation strategies increases, so has the number of projects and investment into carbon sequestration. To have a project, you need to have a source of CO2 and a place to put it, or a so-called sink. Ideally, they're in the same geographical location, but often they are not. So you have primary sources such as industrial facilities, petroleum refineries, chemical manufacturers, etc. And those sources need to be coupled with a sink. And we kind of talked about what some of those sinks are, such as depleted oil and gas reserves and unminable coal seams. A lot of what we look for is deep saline aquifers, which allows for this compressed CO2 to get dissolved into the brine solutions that are found at depth. And those locations can be across the country, and I have some slides that focus more on the locations of the sinks. So let's take a look at US-based CO2 sources. So nearly 60% of emissions come from power plants, typically coal-fired power plants, with an average emission of 1.2 million tons per year. And there's over 1,300 plants across the US. Emissions like these require a higher degree of treatment prior to sequestration to get rid of impurities. Cleaner sources of CO2, such as those from ethanol plants and paper production, are much less costly to clean because they have significantly lower volumes. The data here is the most recent that's been provided to EPA. This is 2020 data, and 2023 data should be available later this fall. These are the locations of the source, and this map comes from Carbon Solutions, who uses public data from emissions reporting and breaks down the different types of industrial emissions along with their volumes. You can see an uneven distribution of where emissions are found, but how they're mainly concentrated around the most populated areas of the country. Now that we know how much CO2 we're looking to store and trap, where can it go? Areas shaded not in blue does not have the proper geology for storage. It's either mountainous regions with volcanic or metamorphic rocks near the surface, or does not have the proper depth of porous rocks for sequestration. Because sequestration requires CO2 to be stored at a supercritical capacity, it needs to be buried at a significant depth, usually at least 3,000 feet. So much of the country qualifies based on this map. Looking locally, however, a storage site must have not only the proper depth, but a proper seal to prevent leakage from both above and below the storage zone, meaning there needs to be thick layers of low permeability rocks, such as shale, above and below the injection zone. Granite is often used, the basement, as the lower seal, provided there's not significant faulting, which could lead to induced seismicity, which is a concern for storage sites. At an even more local level, a way to prevent migration from the project property boundary is either through a fault, arch, or overlying strata, and the overlying strata can form a capillary trap, allowing the CO2 to dissolve in the formation fluid. Also, the area needs to have minimal penetrations into the storage zone and the confining units to help prevent against leakage. Some of the things to note is the locations that have the best geology are also the ones that have the most oil and gas production, which is what you're trying to avoid when it comes to penetrations into both the seal and the storage zone, as each penetration into those zones has a potential to leak. Looking directly at the Midwest, specifically EPA regions 5 and 7, the Midwest obviously has a much lower volume than the US overall of CO2 emissions, but a higher percentage comes from power plants, which is generally a harder CO2 stream to treat when it comes to sequestration. And for some reason, there's a higher production of metals than average across the US, which also has CO2, dirtier CO2. As far as source locations, the highest emissions in the Midwest are related to the urban areas around Kansas City, St. Louis, Chicago, Detroit, and the Twin Cities. And as we can see here, the sink locations don't generally align with many of the major metros in the area. In the Midwest, the Michigan Basin and Illinois Basin and the mid-continent are suitable for CO2 storage, with those areas currently having permits submitted to EPA, and many additional projects are being announced and developed. Recent data show that there is significant growth in the number of projects that are being developed. In the US, the majority of projects are in the Gulf Coast, and you can see the comparison of capture projects to storage projects, suggesting that many projects are being planned to be hubs with multiple sources of CO2 being brought in for injection. Can really be conceptualized at any piece of the systems of capture, transport, and storage. We're focused mostly on storage, but an emissions facility needs to do the capture and cleaning of the CO2 of its impurities, and then after that, it needs to be compressed into pipelines or have another conveyance to a storage facility. There are lots of emissions in locations where storage is not accessible or possible, and also smaller sources where economics don't make it sense for them to be their own operator. So it can be directed to a storage hub facility where multiple wells inject the compressed CO2 into the subsurface. If a facility has its own storage complex, typically only those with a very high volume of CO2 where they can skip the transportation piece and only have on-site pipelines. Those are going to be the most economical for facilities to be built. Point source carbon capture involves collecting CO2 emissions directly from large industrial facilities such as refineries, power plants, or cement factories. These methods target specific emission sources where the CO2 is highly concentrated, making it more efficient to capture. The captured CO2 is then transported to an absorption unit where it is dissolved into a chemical solvent, typically an amine-based solution. The CO2-rich solvent is then heated, causing the CO2 to be released from the solution, leaving behind the original solvent for reuse. The CO2 released from the solution is then compressed into a dense liquid state, meaning a supercritical fluid, and this facilitates transportation and storage. The process is very energy intensive and would be best co-located with renewable or green energy infrastructure. Compression is key because not only does this process reduce the volume of CO2 by 97%, which allows for efficient storage as a supercritical fluid, but also is important for consideration in the carbon credit offsets, which goes into the accounting for the amount of energy used and what type to keep the project honest. So regarding transportation, pipelines are the most efficient way to move CO2 over long distances within the footprint of a storage facility between the compression and the wells. The long distance pipelines face significant public opposition. A CO2 pipeline would likely mean new lines that may or may not follow existing right-of-way, and new lines would need to be constructed due to the corrosive nature of CO2, since it wouldn't be able to be used with existing infrastructure. For smaller scale projects such as pilot projects or demo scale projects, trucks or rail transportation may move smaller volumes effectively with the CO2 stored in compression tanks that could be carried on existing rail or highway infrastructure. Ship and barge transportation can be economical along coastal or intercoastal areas or along navigable rivers such as the Columbia, St. Lawrence, or the Mississippi. Of course, nearly any facility would need a combination of transportation types to connect all sources to sink locations. The final piece of a carbon storage project is the injection well system itself. As mentioned, these wells are very deep and in some cases over a mile or more into the subsurface, with multiple strings of casing that are cemented into the subsurface to prevent leaks. Special materials are needed for the cement and casing and tubing that are resistant to corrosion from the CO2. There are multiple redundant monitoring systems in place, and the overarching principle of any injection program is to protect the underground source of drinking water, also known as the USDW. So to get started, before a permit can be applied for and compiled, a feasibility is done to determine facets related to community support, as just last year, a CO2 pipeline project folded due to its public opposition. So community support is key for these types of projects. Early cost assessments are done to help set a budget for the project to know if there's adequate capital investment. Then we review the regulatory environment. Some states have already prohibited any sequestration projects, and others are trying to get regulatory jurisdiction from the federal government to provide as much support to local industry as possible. Then, if all community support, money, and a favorable regulatory environment are in place, we can look at the geology to see if it's suitable, reviewing the depths that would allow for supercritical storage, the porosity and permeability needed in the storage zone, as well as seals. We will review the existing information, determine if there's confining units, and look for risks of leaks related to geological structures such as faults and other artificial penetrations. If everything looks good and the storage operator wants to move forward, we'll go into a deeper dive into the regional and local geology, working with the operator to find contiguous property for pore space ownership. So during this process, we would do site characterization, extensive mapping of the area based on all known data. An area of review would be created, which projects the model of how the CO2 plume and pressure font interacts with any penetrations in the area. We would address any wells that were open or improperly plugged within that area of review, and to ensure that we eliminated potential leaks. We would go through the design and engineering of the well and all the completion details related to it, set up operational plans regarding rate, pressure, flow, how information would be recorded, and what the testing and monitoring plans would be, and then set up a number of emergency plans for future use, emergency plugging, post-injection site care, financial responsibility, and environmental justice. And all of these pieces would come together to create a permit application, which would then go to either the EPA or a state RAM program. Once a permit would be published, the operator would have a set amount of time to begin construction. And then once the construction was complete, there'd be iterations of how the plume would be expected to travel. Area of review would be updated based on local information that would be derived from the drilling of the wells. And then ultimately EPA or the state-ran regulatory body would give approval to inject. So once a project becomes operational, there's ongoing monitoring and testing that gets reported to a regulator quarterly, up to annually, depending on the type of reports. Overall, many things such as injection rate and pressures are monitored with SCADA systems with 24/7 monitoring. Many wells have instrumentation downhole to monitor any microseismic activity and pressure changes related to the volume of injection. Models are constantly refined and compared to the facility performance to reduce risks and unknowns related to the failure in the system. Once the project has lived its design life of anywhere from 20 to 50 years, then there's a post-injection site care plan, and that timeline can vary, but it's similar to post-closure requirements for landfills and other waste facilities. Ultimately, when the conditions are met, wells would be plugged and the site is abandoned. I've mentioned containment multiple times and ensuring there are no releases, but why? First, we want to avoid leaks out of the storage zone that could migrate into the usable drinking water or USGW. We also want to avoid any releases to the surface where there could be an environmental and health and safety issue, as well as a loss of containment, which would allow emissions to escape into the atmosphere. How do we monitor for a loss of containment and ensure there's a low risk of failure? Well, through multiple layers of monitoring at the surface, in the atmosphere, within the subsurface. There are multiple valves at the surface that are monitored to track flow and pressures, multiple casings that are monitored for downhole well systems, which monitor corrosion and pressure changes within the entire system. All of this data is collected on multiple fronts around the clock and will alert operators of any unexpected changes in volume, flow, and pressure. Lastly, each injection well is surrounded with monitoring wells, both up gradient and down gradient of the injection zone, above the injection zone, and in the lowermost drinking water zone, looking for changes in pressure or geochemistry through instrumentation and physical samples. From project conception to injection can take several years and a significant investment prior to any cost recovery. During the pre-permitting phase, and even after due diligence, it may be determined that a test well is necessary to collect local data to have on-site information related to the volume of pore space available to inject into and the storage potential of the area. And if it isn't feasible or there are other red flags, a project might be abandoned even after all of this early investment. The more time spent on the application upfront will likely result in a faster review by the regulator. So engaging with the regulator early and often in the application process is ideal because they are the ones who will give the green light for construction. Construction for a facility like this can take 12 to 18 months with a minimum of 5 to 7 fairly significantly deep wells needed at a minimum for a single injection well project. On top of civil site improvements and all the instrumentation. After the facility is constructed, there's a period to ensure that the dynamic model is accurate and is refined to match site conditions. Then the facility is operational for the life of the design, and the project enters the post-closure period with ongoing monitoring. So where are we now? Currently in the US, there's about 5 million tons of permitted storage in operation, with an additional 12 million or so that was recently permitted and should be under construction soon. This only adds up to about 0.5% of the annual emissions that can be captured by currently permitted infrastructure. So we need to massively scale up to reach climate goals using carbon capture and storage. In the Midwest, the Class 6 activity has been ramping up. Many projects are in the works within the Illinois basin, and Illinois and Indiana seem to dominate where projects are being designed at this point. and it's likely due to the larger sources in those areas and the favorable regulatory climate. As far as capture projects, the Midwest is gaining momentum for capture projects, with many launching in the Corn Belt connected to biorefineries and ethanol plants. There are relatively large sources of CO2 in Iowa, but they lack the suitable injection zones that are available in most of the state doesn't have suitable injection zones. So financial project considerations. Altogether, what does it cost? Capture costs can vary, with higher costs of capture related to power production, iron and steel and cement captures, and all that costs will depend on how much cleaning is required of the CO2. The cleaner sources of CO2, such as those at ethanol plants, are closer to $20 per ton for capture. Transportation costs vary significantly, with pipelines being the cheapest, but higher costs related to truck transport. Finally, the cost of storage is generally thought to be around $5 to $10 per ton. Government tax credits are available to those who meet the criteria found in the tax code guidance. Well, the last things I want to talk about is community engagement and environmental justice. One of the priorities of EPA over the last 5+ years has been environmental justice, and they recommend that potential developers reach out early and often to their regulator. It's beneficial to include the community early to make sure that they understand what the project would entail and what community benefits will come from the project, as there's a huge push within the EPA for environmental justice, and that will be heavily evaluated as these projects are being developed and permitted. Happy to take any questions, but also feel free to reach out to my colleagues and visit our website for more information. We have several webinars about carbon sequestration on our website and our YouTube channel. I'm happy to take any questions. Thank you.
Awesome. Thank you, Carrie. Yeah, if people have questions, we have the Q&A function is set up here, or you're welcome to raise your hand and unmute yourself.
Thank you very much. It's very informative. The costs you are showing, are those with or without the tax credits, the IRA tax credits?
Those are without.
Okay, so tax credits would just lower those.
Yes.
Okay,
but the tax credits are directed to those who sequester the CO2, not necessarily those who capture it. So I think there's, questions lingering on how the economics will work out for these types of projects.
Sure. It's an influence on the cost of their product being captured CO2, and someone will buy that product because they can make money storing it. That's the idea behind this, right?
Yeah. I think so. I think some of the developers think that they may not be buying the CO2. I don't know.
I know you kind of highlighted community support there at the end. Have any of the projects that you've been involved with, has there been pushback from the community or any other projects that you're aware of? And if there is, what's their main concern? Is it, drinking water contamination or something else?
I think it's concerns about releases. I think there's probably some amount of, not in my backyard type thing. One of the projects that we've been involved with is out in the California Delta area, and they have fairly strong community support. They've engaged with the community leaders very early in the process to try to get them on board regarding, all the benefits that it'll bring, cleaner air. They're even engaging them to do some of the monitoring that's required to, have better community buy-in.
Awesome, thank you. Looked like we had something that came through on the Q&A. Says, I understand that long pipelines are unpopular to the general public. That said, if they are being used to transport CO2 for sequestration to benefit the environment, rather than for pulling things from the earth? Has there been a difference of opinions there?
Not that I'm aware of. I'm somewhat familiar with the pipeline project that was in Iowa that was abandoned, and that was abandoned, I think, primarily due to lack of grassroots support. And I think there were concerns about landowners having, their right of way going through their property, and they just didn't agree with it. And the project was scrapped, from what I understand.
Jeff, thank you. Brian, assuming you meant to put your hand up again.
Yeah, I did. I'm familiar with some of the modeling that was done for risk management, risk analysis for like chlorine and things like that. Is there a similar requirement for CO2? Because I guess the biggest danger was, a leak under high pressure. And carbon dioxide is so heavy, you're going to get like a slab of it forming, stays close to the ground. And I mean, the potential disaster is enormous. But is there modeling being done to assess that, the potentials, and you have to balance risk with benefit, right? That would seem to be a very difficult, weird thing to have to do.
I primarily focus on the subsurface, so I can't really speak to what's being done to model the pipelines. I know in a lot of cases, new pipelines are just really a big challenge socially. So I think most facilities that are being developed are trying to be developed on private property, and really reduce the use of pipelines or new pipelines. But I'm sure there's work being done regarding modeling some of those risks, but I'm not familiar with it.
Speaking of pipelines, for the projects that you've been involved with, have they mostly involved like on-site pipelines, or have you had experience with any that have kind of transported, I guess, off-site and to somewhere else?
We're involved in a number of just kind of feasibility projects right now. So a lot of projects haven't gotten to that stage. Really, there's only, I know I had a number in my presentation on how many projects there are nationwide. There's not, let's see, there's only 87 projects currently being considered in the US. And we're involved in a number of feasibility projects, but only 2 permits. The majority of permits, I believe, have been submitted by like major oil and gas companies who have their own source and have their own land. So, that's not as big of a concern. These hub projects where they're trying to bring in CO2 from multiple sources, one of the ones we're involved with is actually going to be using a barge to get around some of the pipeline needs. So their source is located on a navigable waterway, and they're going to be barging the CO2 to the sequestration site and then using pipelines on their own property to distribute the CO2.
I assume the CO2 would be just like in tanks on the barge, or okay.
Yeah. Compressed.
And yeah. And then with the sites that do have their own pipeline, like you said, most of the existing infrastructure can't handle the CO2. So are they putting in, brand new piping? Are they kind of retrofitting what they already have, or no idea?
I couldn't say. I mean, I think they could probably, they might be able to put liners in existing pipes. I really am not sure. The big thing is CO2 is highly corrosive, and so they need special steel and corrosion resistant steel to be able to set up new facilities.
I have one more question. So if others have questions, send them in. Otherwise, we'll let you all go a little bit early. But what have you seen as like the most common, I guess, capture method? I know you're more involved with the storage, but do you know like what most people are doing in terms of capturing the CO2 before storage?
The capture projects are fairly, I mean, limited. And again, I think they're primarily aimed at some of the larger emitters. I know there's a big drive to do capture of ethanol, produced CO2 because it's fairly clean. What they're doing with that captured CO2 at this point, I'm not entirely sure, since there's not a good location to inject it. So I'm not all that familiar with the capture process.
Yeah. Okay.
Apologies to the air people.
I know, I'm an airhead. I had to ask.
So I should be telling my grandkids to major in geological engineering is what I'm thinking.
If this is gonna take off, I think we're gonna need somebody to build a bunch of rigs.
Yeah, there's not enough geological engineers and geoscience people out there to do all the work that's needed. So anyway,
Yeah,
That's for
sounds
sure.
like we're gonna need a lot more these kind of projects to hit any climate goals based
Yeah.
on your graph there.
It was really astounding when I kind of did a comparison and found that we're only, even the stuff that's been permitted but not even constructed yet, and we're at 0.5% of emissions. And that's reported emissions, not necessarily all emissions.
Excellent. Well, thank you very much, Carrie. Unless I see someone's hand pop up or something come through Q&A here shortly. Thank you everybody for attending. Thank you, Carrie, for the presentation. As usual, assuming that Carrie's okay with it, we'll have a PDF of the presentation up on our website that you guys can go back and reference. Again, our next monthly meeting is on September 12th. And that is on some RCRA regulations, tips to minimize your waste. So again, thank you everybody for attending. Thank you, Carrie, for presenting, and we'll see you next time. Thanks, everybody.
thanks a lot.